Oh, and I'll do my best to post the recording to my YouTube channel. Okay, so let's get into esters. We've covered acid chlorides, we've covered acid anhydrides. Now we're going to get into esters. Then we'll make our way into amides and eventually to nitriles. But with esters, how do you make an ester? Well, there's a few ways you can do it. One way is to use this two-step process where you take the carboxylic acid, you treat it with sodium hydroxide, and what that's going to do is it's going to rip off the acidic proton from your carboxylic acid, so you form a carboxylate, and that carboxylate is going to react with your electrophile, which here they've drawn as iodomethane, in an SN2 fashion. So you have your nucleophilic attack followed by loss of leaving group, and that's a way to make an ester. This part here, it kind of reminds me of a Williamson ether synthesis. Obviously, you're not making an ether, you're making an ester, but it's like the same kind of rationale. You have an oxygen with a negative charge, and then you have an SN2 reaction. So that's one way of making an ester, is to take a carboxylate and react it with an alkyl halide. However, there is another way that's very important for organic chemists to know, and that is the Fischer Esterification, one of the most important reactions in organic chemistry. I'm going to highlight the mechanism down here. You need to know the mechanism of Fischer Esterification. Any kind of standardized exam in chemistry loves to ask questions about Fischer Esterification. So here it is. What we do is we take a carboxylic acid. Okay, we take our carboxylic acid and we react it with an alcohol. Carboxylic acid plus an alcohol in a catalytic amount of acid, and we end up producing an ester, and we drive off water. Now, if this reaction is in equilibrium, what we have to do is we have to harness the power of Le Chatelier's principle to drive the reaction towards the ester, meaning we have to remove water from the reaction mechanism. I'm going to show you how we do that in just a second. But before we do that, I want to take a look at the mechanism. Now, if you think about methanol, methanol is not a strong nucleophile. It's a weak nucleophile. Is a carboxylic acid electrophilic enough to react with methanol? The answer is no, it is not. However, if we protonate it, right, if it gets protonated by the acid, and this is just a shorthand mechanism to make an oxonium ion, if we make an oxonium, that's a lot more electrophilic, and then our methanol can come in as a nucleophile like this. This is actually the first and second steps of the mechanism that are shown on this slide. The first step is the proton transfer, which renders the carbonyl group more electrophilic. Now that you've made it a very powerful electrophile, the methanol can come in and do a nucleophilic attack. Now, again, study this mechanism carefully and notice that every single step in here is in an equilibrium. Everything's in equilibrium. So there's got to be some driving force to push this reaction forward. And we notice that in this step right here, so we end up losing water, so minus H2O. So let's go back. We have our proton transfer in the first step. The methanol comes in as a nucleophile, and then we do another proton transfer to end up with this uncharged species. Now we have to convert one of these hydroxyl groups. It wouldn't matter which one, they're identical. We have to convert one of those into a leaving group. What do? We have to protonate it. Then you lose water, where I have the blue circle and the minus H2O sign, and then you just do the deprotonation of the oxonium, and you end up with the ester. So, if you're wondering, and I've gone over this many times in class, like why are you writing this as your acid? Because this is usually done in the presence of a strong acid like sulfuric acid. But what happens if you take sulfuric acid and you put it in methanol? What's going to be the major acid in the solution is going to be the protonated form of methanol. That is why they don't draw sulfuric acid as the acid. They draw this, the conjugate acid of methanol, as being the acid. And we have the hydrosulfate ion, because this is our major acid in solution. So if you were to draw sulfuric acid, I guess there's some of it in the solution, but it's not what is going to affect most of the proton transfers. So if you're wondering, how do you end up removing this water? If you're in methanol and water, well, water and methanol are miscible. But you can mix them together. You can mix ethanol and water, so you can certainly mix methanol and water. How do you remove the water? Well, the way we do it is to use a special piece of glassware. It's called a Dean-Stark trap. Let me kind of zoom in. I don't know how well you can see this on the slide. I'm looking at it very carefully here. But the idea is that you have your reaction. So pay close attention. It's not tricky, but it's interesting. So you have your reaction mixture. Where's my red pen? Your reaction is in here. So there's the reaction. That's where the esterification is taking place. You notice that this is a hot plate. Okay, so this is a hot plate. And what you do is when you run the Fischer esterification, you run it so the reaction is refluxing. Now, what refluxing means is that it's at a constant boil. Well, if you're thinking, well, how can you have something at a constant boil? Because then all the vapors are just going to escape. No, because you have cold water. So there's cold water from the faucet running into this glass condenser here. So when the vapors, I'll use my yellow highlighter, when the vapors come out of here, they get trapped in here and then they come back down. Okay, so that's why it's called reflux. The vapors go up, then they come down. But you notice that there's a crook in this glassware, isn't it? It's not straight. It goes up and then it's got a bend in it like this. So that means the vapors, when they get caught here, they condense and they end up in this part right here. And you notice that there's a little stopcock right here. So stopcock. Okay, so let's think about it. What are the vapors that are coming down? If you're using methanol as your alcohol, the vapors that would be coming down would be the vapors from methanol and water. But luckily, water is more dense than methanol or ethanol. So what gets caught in this glass tube here, on the bottom is going to be water, and on the top is going to be methanol. And eventually it gets so full that the methanol will start spilling back in here, but you can open up the stopcock to drain the water out. You can actually throw the water, just drain it and throw it in a flask and throw it down the drain. Okay, it doesn't matter. Now, I'm not going to quiz you on this. It's not going to be a question on your exam. I just wanted to show you how this thing works. And if you want more information, you could Google it. It's called a Dean-Stark apparatus. Okay, and I'm not sure if I spelled Stark correctly, but either way, the Dean-Stark apparatus, which is a very clever invention, very simple, but very, very clever way to remove water. And that is how you drive the Fischer esterification forward. Now, a little more information about that mechanism is you might be wondering, well, how are they sure about this mechanism? And in this class, we don't talk about radio-labeled experiments a lot, but hopefully you remember isotopes from mass spec, for example, and just from Gen Chem 1 and this class a little bit. But if you put a radio-labeled oxygen, so that means a higher mass isotope of oxygen in a methanol molecule, and then you look at the structure of the ester that's produced, what we find when you examine it by NMR is that the oxygen that was radio-labeled is incorporated into this, carbon-oxygen bond here. And so that's further proof for the mechanism of Fischer esterification. Can't stress this enough, my friends. Going back here again, you've got to know this mechanism. Know this mechanism. Very important mechanism, Fischer esterification. All right, there we go. So if we covered Fischer esterification, next, hey, here's a reaction that we looked at in the last, 45 minutes ago. Reaction of an acid chloride with an alcohol and pyridine to form an ester. And I said the reason why you have to have pyridine required to neutralize HCl produced. So besides the ester, you also end up with pyridinium chloride. So let's write up the structure of pyridinium chloride, which is this the conjugate acid of pyridine and the chloride. Okay, so this is something that we covered already back in section 20.8, so we won't spend too much time on the same thing twice in a day. Next, we have a question. All right, and this is a bit of a brain bender. It asks you, how many ways can you make an ester? We learned a few ways to make esters today, and let's review. So if you want to take benzoic acid, this carboxylic acid, benzoic acid, and we want to make this compound, which would be ethyl, right? Ethyl benzoate. Ethyl benzoate. I'll just throw this out there to my students. Again, we learned 3 ways. I wouldn't expect you to be able to regurgitate all 3 of them this second. Could anybody tell me one that they maybe have in their mind, a way to make an ester? Even if it's anything that we've learned would be fair game. What's a way that we could make this ethyl ester, this ethyl benzoate from benzoic acid?
Maybe excess MeOH?
So so using sodium hydroxide, so what you're saying is do the deprotonation to make the carboxylate? I agree. I think that's a great way. Why don't we write that down? So first one, you don't need excess, since you only need to rip off, for every 1 sodium hydroxide, it's going to rip off 1 of those protons that I have in the red circle. So you can just write, first step would just be sodium hydroxide. And then the second step, since we're adding an ethyl group, you could pick ethyl iodide, you could put ethyl bromide, you could put ethyl chloride, I don't care. I'll put ethyl iodide. Since I have expensive tastes, alkyl iodides are the most expensive of all of them, and bromides are significantly cheaper, and chlorides are cheaper than dirt, but they don't work as well. What's next? What about Fischer esterification? If we want to use the Fischer reaction, and if we're trying to make an ethyl ester, let's go back here to Fischer. If we want to make a methyl ester, we have to use methanol. If we want to make an ethyl ester, our solvent has to be ethanol. So let's go back here. We'll do Fischer. So our solvent would be ethanol. Then what else do you need for a Fischer? You need a catalytic amount of acid to promote that. So I'll just write H plus in brackets. And then just like when we made the acetals, we always write minus H2O, just so the reader knows that we're losing water in the Fischer esterification. And one other way that we learned is to proceed through an acid chloride. So to start with a carboxyl group, and number 1, treat it with thionyl chloride, SOCl2. That makes the acid chloride. And then number 2 is to treat it with, in this case, you want ethyl ester. So you would use ethanol. And of course, you need pyridine to neutralize the HCl. So those are 3 different ways that we've learned to make an ester. All right, that's a lot of ways to make an ester, my friend. I want to draw your attention to Fischer again, and you're going to see we're going to talk about esters a lot. Now, Le Chatelier's principle came up earlier in the lecture, and it's going to come up again now, okay? Because what was the driving force behind the Fischer esterification, right? It says it is an equilibrating process. The whole thing is in equilibrium. In order to drive the reaction toward the ester, you've got to remove the water, right? What would happen if I did the Fischer reaction, or not the Fischer esterification. Let's say I just combined an ester with a ton of water. Okay, if I had a pile of water, that's going to push the reaction back towards the carboxylic acid. So we can harness the power of Le Chatelier's principle in order to hydrolyze an ester. So now we've looked at the formation of an ester, Fischer esterification, and those 2 other methods that we saw in the last question. So now we're going to talk about blowing an ester apart, taking an ester and bringing it back to a carboxylic acid. There are 2 ways we learn how to do that. Number 1 is in base. When you hydrolyze an ester in base, it's got a fancy name. We call it saponification. Another very important reaction. You must know the mechanism of saponification. I'm going to go over it with you. But you can imagine that if you have sodium hydroxide, you have the sodium cation, the hydroxide anion. Well, hydroxide is definitely nucleophilic enough to attack the ester. All right, it's going to attack that ester to form a tetrahedral intermediate. And then after a couple of steps, you can form a carboxylate. Now, if you're wondering, why do you need acid in the second step? Well, notice what I just said. I said you don't form a carboxylic acid after the first step. You form a carboxylate. There's no way you could form a carboxylic acid with just sodium hydroxide, because if you did form the acid, it would be deprotonated by the strong base. And so you need the second step to do the protonation to form the carboxylic acid. Let's take a look at the mechanism. Here it is. It's not very long, but this is one of the most crucial mechanisms. Know this mechanism. Move that bus. Okay, very important mechanism in organic chemistry. First step, just a nucleophilic attack. Right? We know the ester is susceptible to nucleophilic attack by a strong base, strong nucleophile like hydroxide. We form the tetrahedral intermediate, and we lose the alkoxide. But again, think about this very carefully. You could not make a carboxylic acid in the presence of a strong base. That's impossible. So either the sodium hydroxide or the conjugate base or just the alkoxide that you lose is going to rip that proton up. So after the first step, the treatment with the sodium hydroxide, you end up with a carboxylate. Then in the second step, so step 2, you treat it with H3O+, and that is what makes the carboxylic acid. That's what's shown, or sorry, I don't even have that shown on here. Anyhow, so that's saponification, all right? The next thing that you need to know is the acid hydrolysis of a the acid hydrolysis of an ester. It does not have any tsatsi name, right? The hydrolysis of an ester in base is called saponification. The hydrolysis of an ester in acid has no name. It's just called acid hydrolysis of an ester. Nothing uber exciting. Okay, so what do we do now? We're going to take the ester and we're going to put it in aqueous acid. So now you've got a ton of water in here plus a little bit of acid, right? That's what this means. And so if you have a pile of water over here plus your ester, it's going to push the reaction towards the carboxylic acid. It is the exact reverse of the Fischer esterification. Again, we just harness the power of Le Chatelier's principle, and we put a lot more water in the reaction mixture now that drives it towards the carboxylic acid. That's all we're doing. If you understood the formation of the ester in acid, the Fischer esterification, then you're going to understand the mechanism because the mechanism of the hydrolysis in acid, because it's the exact reverse of the mechanism. It's the same thing, just in reverse, which is based off of something called the principle of microscopic reversibility. Let me tell you something. If you know the mechanism of a reaction in one direction, if you look at that reaction in reverse, if it's something that's in equilibrium, the mechanism is always the exact same arrows, just in reverse. That's all it is. Okay, there's no brand new mechanism that you've got to conjure up. It's not a thing. All right. So let's take a look at the mechanism. Again, it's just the reverse of what we looked at. Think about it. When we were doing Fischer esterification, what was the first step? It was the protonation of the carbonyl to make an oxonium. Then you had the methanol come in. Anyhow, I'm not focusing on the right thing. So now we're in aqueous acid. We protonate the carbonyl to make an oxonium, and now water is going to come in as our nucleophile. Well, hold on. It was methanol that was our nucleophile the last time for Fischer, but no, now we're using a huge amount of water. It's all based on equilibrium. So water comes in, we do a proton transfer, then we protonate the alkoxy group to make this oxonium, which can cause methanol to leave. It's not loss of water now, it's loss of methanol. And then we end up doing a proton transfer in the end to regenerate our carboxylic acid. So let's write on here know this mechanism. All right, know this mechanism. The mechanism of ester hydrolysis and acid. So to recap, I don't really have a lot of space here. I'll just write it here. We can take a carboxylic acid. Let's write here. A carboxylic acid plus an alcohol, okay, with a catalytic amount of acid, that can form an ester. Okay, that makes an ester. We'll do that. And that is called Fischer Esterification. Once you have an ester, you can hydrolyze it in base. Let me write this like this. You can hydrolyze it in base, sodium hydroxide. That's going to give you the carboxylate, okay, which you can protonate, with treatment with H3O plus to make the carboxylic acid. But this reaction here, this is called saponification. If you're wondering, this is how soap is made. It's the hydrolysis of animal fat or esters, or oils, okay, that come from plants. Or you can hydrolyze it in acid to make a carboxylic acid directly. This has no fancy name like saponification. It's just called the acid hydrolysis of an ester. Every mechanism, this one, and this one, you need to know, and of course this one too, which is just a proton transfer. Those are the things that come up in standardized exams all the time in organic chemistry. So with all that in mind, let's talk about a few more reactions of esters. This one is called aminolysis. You think about what aminolysis means. You've got amino, right? You have an amine, and then you have lysis. Lysis just means you're breaking something, right? To lyse something, right? Glycolysis, right? Anyhow, so an ester can undergo aminolysis. So if you take an ester and you treat it with an amine, you can make an amide. And it says here that the equilibrium does favor the amide formation because amides are more stable than esters. However, this reaction doesn't have a ton of synthetic utility. It says it's limited because the reaction is so slow. There are better ways to make an amide, right? A more effective way would be to use an acid chloride, like we looked at before. If you take an acid chloride, and this is what we learned in section 20.8, you can take an acid chloride, treat that with excess ammonia, and that is going to give you a primary amide. But this would be fast, and this is very slow. Can it be done? Of course. Yeah, it can be done. But, as organic chemists, we usually try to find the best, most expeditious way to make a compound. Next slide is just a review. This is a reaction that we learned way back in the alcohols chapter. So this goes back to chapter 12. We said if we took an ester, treated it with excess lithium aluminum hydride followed by water or H3O plus, we could make a primary alcohol. Two equivalents of the reducing agent. That's why we write excess. And it says we get two alcohols. So we end up making one alcohol. Where's my blue pen? From this portion of the molecule. And then we end up making the alcohol from this portion of the molecule as well. And again, the mechanism is just like we saw the reduction of an acid chloride with lithium aluminum hydride. Let's take a look at it here. First step is just the nucleophilic attack of the hydride. You make the tetrahedral intermediate. You lose the alkoxide. You form an aldehyde in situ, which just means in the reaction. And then, of course, if you treat an aldehyde with lithium aluminum hydride, it's going to make a primary alcohol. And so that's really all there is here. And again, here they have water drawn in. Water drawn in. You could use hydronium. Either way works. Both work well, depending on the situation. Well, let's talk about one more new reagent, and then we're going to try some practice that has to deal with esters. So one new reagent in this section, and this is a very commonly used reagent in organic chemistry. It's not some kind of you know, something that's never used or anything. This is used very frequently. This is called dibol, or diba is the way our book calls it. When I was in graduate school and when I was a chemist, you know, an industrial chemist, I never called it this. I always called it dibol H. But apparently nowadays, I guess they call it DIBAH, diba. Anyhow, they both mean the same thing, right? This is an isobutyl group here. So isobutyl. So what that stands for is diisobutyl, butyl, aluminum hydride. And diba, or dibol as I call it, is nothing more than a more selective way of reducing an ester. It's a way to stop it at the aldehyde. With what was it? With the acid anhydride and the acid chloride, the way we stopped at the aldehyde was using lithium tri-T-butoxy aluminum hydride. Now it's a different hydride delivery agent. So dibol followed by water gives you the corresponding aldehyde, and of course you also liberate the alcohol. There's no mechanism for this in the book, so don't worry about a mechanism for this reaction. It's not in my slides. That's because it's not in the book either. So that's in kind of one. I would say that I told you at the beginning of the lecture, I would kind of point out when things were kind of, you got to remember this. Yeah, so what I said was if you had an acid chloride, if you had an acid chloride or an anhydride, let's just remind ourselves of this. And this is just review. I said that if you treat this with lithium, aluminum tri-T-butoxy hydride, followed by H2O or aqueous acid, that would stop either of those at the aldehyde. Okay, you'd stop at the aldehyde. But for an ester, you can't use that. You have to use this special reagent. Dibol, anyhow. And the last reaction in this section is another one that we saw back in chapter 12, and we've even looked at it today, something close to it, which is where you take an ester, treat it with excess Grignard, followed by treatment with water or aqueous acid, and you end up with a tertiary alcohol. And that's because you end up making a ketone along the way. And this is the second time I've showed you the same mechanism. I showed you this back in chapter 12. I'm showing you it again now. You get one nucleophilic attack, you lose your alkoxide, you make a ketone, and a ketone can, of course, undergo nucleophilic attack by a second Grignard. Then you have water, and again, you could draw this step with aqueous acid, hydronium. That would work too, and you end up with a tertiary alcohol. Is that enough chemistry to try some practice? I think it's more than enough. So let's give it the old college try here. We've got an ester in A. We've got an ester, and we want to reduce that with lithium aluminum hydride. So what we end up doing with an ester is we reduce it to a primary alcohol with lithium aluminum hydride. So let's draw that primary alcohol. We'll count our carbons carefully. 1, 2, 3, 4. Right? 1, 2, 3, 4. And then we have our primary alcohol off of there. You also end up forming methanol in this case. So let's scribble that down, plus methanol, because you end up losing that during the mechanism. The next one is a reaction that we looked at in chapter 12. So this goes all the way back to chapter 12. It's just a review. Remember that you add the ethyl magnesium bromide twice because you form a ketone. Then it gets added a second time, and you would end up with, a tertiary alcohol, and you will have added one ethyl group, two ethyl groups, like this. And of course, you would also liberate the methanol, so I'll scribble that over here too. The next one is that reaction that Lindsay brought up. We were talking about ester synthesis. So in the first step, you take the carboxylic acid, which is benzoic acid, and you make the conjugate base, which is a carboxylate. They're not asking for this, but we'll just pencil it in. And then in the second step, you treat it with ethyl iodide, which is a really powerful electrophile. You get nucleophilic attack, loss of leaving group, just a plain old SN2. And then you would end up making ethyl benzoate. practice an ester nomenclature. And the last one, this one's kind of interesting. Hey, I got a question for you. It's a tough question. Tough question. Does anybody remember what a cyclic ester was called? So this is an ester stuck inside a ring. Does anybody remember what that was called? I went over it with you once, I think, before this semester. It had a cool name. Maybe yeah, maybe no. Where are my students? There you are. Anyhow, that's called a lactone. It's a cyclic ester. So a lactone. And if we end up reacting this cyclic ester, okay, remember that the first equivalent of the ethyl magnesium bromide, let's pencil it in. Magnesium bromide, right? The first equivalent is going to attack the carbonyl to make a tetrahedral intermediate like this. Let me just pencil it in here. So we end up with something that's going to look like this, where we have our tetrahedral intermediate here, like that. And then what happens is the leaving group is the alkoxide, right? So you end up forming this double bond, and then you lose this group. That's going to be dangling off there. I'm going to run out of space, aren't I? So we end up with this, where we have 1, 2. So we have 1, 2, and then we have our alkoxide over here. And then you have this ethyl ketone over here. So then the ketone is susceptible to a second nucleophilic attack by a second equivalent of the Grignard. And then after successive proton transfers, you'll have to forgive me because I'm kind of running out of space here. You're going to end up with this as your product, where after protonation, you're going to have an alcohol here, and then you're going to have a tertiary alcohol up here with 1, 2 ethyl groups on it. All right, there we go. So I kind of ran out of space on that one, but hopefully you get my drift on that one. And now I want to take a look at a reaction mechanism, and this is just a lactone. Again, I'm really obsessed with the lactones here, or the author of the book is. We're going to take a lactone, which is nothing more than a cyclic ester, and we're going to hydrolyze it in acid. So this is just the acid hydrolysis of an ester. And in this case, you could call it a lactone. So where do we start? If we have hydronium in solution, hydronium is a crappy nucleophile. Okay, so what do we have to do to render the ester more electrophilic? We have to do a proton transfer. Let's draw what that looks like. Let's draw the corresponding oxonium ion, which is going to look like this. Remember, every step is going to be in equilibrium. So we're going to end up with this. And now we've got a proton on here, positive charge. So now this carbon is super electrophilic. And we also produced water in the first step. I'm missing a curved arrow. There we go. So now water is going to come in as our nucleophile. So let's write water molecule. Here's our nucleophilic attack, like this. And let's draw the intermediate that's formed. So we'll draw it very carefully. A 4-membered ring. We're going to have a hydroxyl over here. And we're going to have an oxonium here, like that. What's the next step going to be? Well, we have to end up losing this part over here to break the ring open. So we can't do that until we remove a proton from our oxonium. So another molecule of water is going to rip off that proton like so. So then we end up with this intermediate. Looks like this. So we have our hydroxyl here and a hydroxyl here. Now we need to convert this into a good leaving group to break the ring open. So we're going to show that as being protonated. So I've got my aqueous acid, my hydronium. I'm going to do a proton transfer to convert that into a good leaving group. Now let's draw this intermediate. So I've converted this into a good leaving group. It's got a positive charge like this. I've got one OH group here and one here. Now, the reason I drew that out explicitly is because my loss of leaving group is going to involve formation of a pi bond and loss of leaving group. Now let's draw what that intermediate looks like. So you can count the carbons very carefully. Look, we've got, let me zoom in here a little bit. We've got 1, 2, 3, and the fourth atom will be the oxygen. So look, we've got 1, 2, 3, 4. On the fourth one, we've got the oxygen, which has the hydrogen on it. And then on atom number 1, you've got a double bond to an oxygen with a hydrogen on it. So that's going to have a positive charge. And then you've got a hydroxyl. Well, you can see what the rest of the mechanism is. The rest is just taking a water molecule and regenerating the acid catalyst. And there you have it, my friends. That's the entire mechanism for the hydrolysis of an ester. Again, a cyclic ester is called a lactone in acid. Ay, ay, ay. Interesting mechanism, but you would want to know, I'll just remind you, and I told you this before, but know this mechanism, very important mechanism. All right. So there we go. Let's move on and talk about amides for a couple of minutes. There's not a lot of mechanisms that we haven't looked at for the amide chemistry. There's really only one or two mechanisms, I guess, in here for amide. So let's just cover some amide chemistry quickly. So far, we've gone through acid chlorides. They were the most reactive. Then we looked at anhydrides. They were pretty much analogous to the chlorides with a couple of nuances. Then we spent quite a bit of time now talking about esters, esterification, so Fischer reaction, then hydrolysis and acid, hydrolysis and base. And now we're all the way down to the lowly amide. Well, the good news is we've already talked about amide chemistry quite a bit. You're wondering, well, give me an example. Well, here's one right here. This is one of the first things we looked at today. Taking an acid chloride, because we talked about acid chlorides in depth, with two equivalents of an amine, and you make a primary amide. If you have a primary amine, you make a secondary amide. And if you have a secondary amine, you make a tertiary amide. And remember that you've got to have two equivalents of the amine. Why? Because the second one is going to neutralize the HCl that is formed. Anytime you're using an acid chloride, you've got to neutralize the HCl. Well, here's a new reaction for you. And this is the hydrolysis of an amide in aqueous acid. It can be done. Okay, it can be done. The formation of ammonia is the driving force here because it's such a weak acid compared to hydronium. But it is a slow reaction. Okay, slow, requires high temperature, but again, it does work. You can hydrolyze an amide to a carboxylic acid this way. Here is the mechanism. Now, I have my notes right in front of me. Nope, I didn't have it here. Okay. Yeah, I guess there's one more point I wanted to make. Yeah, the product is favored because in the end, you end up with ammonium, and ammonium can't act as a nucleophile. So the reaction cannot go in the reverse direction. I'm paraphrasing what I said already, but what I have on my notes in front of me, and I'll write it here as proof, is I will not ask you this. Will not ask this mechanism on a quiz. The reason why is because I figure we have enough to remember with ester hydrolysis and everything that we've covered already. And if you understood the acid hydrolysis of an ester, I bet you could all draw this mechanism without my help. It starts with a proton transfer to render the amide very electrophilic. Then water can come in, attack as a nucleophile. We do two proton transfers in order to end up protonating the amine, converting it into a good leaving group. It leaves, and then you do another proton transfer in the end. And once you end up with ammonium, this is just right here, not a nucleophile under any circumstances because the lone pair is protonated. And so this reaction is not going to be reversible. Anyhow, that's enough about that. What else? Hydrolysis of an amide and base can be done. But check this out. Even worse, it says even slower than in acidic conditions. It does work. You can do it, but it is very sluggish chemistry. And of course, after the first step, you don't get a carboxylic acid because you're in base. You end up with a carboxylate. And then after the second step, you treat it with acid, and that's what converts it to the carboxylic acid. Now, the mechanism. It's analogous to the base catalyzed hydrolysis of an ester. Same thing. You get the nucleophilic attack because hydroxide is a very powerful nucleophile. You lose a leaving group. This time your leaving group is amide. Remember that NH2 minus, that's called the amide ion. Okay, the amide ion leaves, but the amide ion is a very strong base. Strong base. And so it's going to rip the proton off of that acid to produce the carboxylate. And then, of course, in the last step, you treat it with H3O+, just like you saw in the last slide, and that gives you the carboxylic acid, just like that. All right. Yeah. Okay, one more reaction of amides, I think. Then we'll try a practice problem. Last reaction, and this one is the reduction of an amide to a primary amine. Very strange reaction, very different from all these other reactions that we've looked at today. It even tells you here the mechanism is quite different from the others. Another thing I'll show you is that, first step is lithium aluminum hydride. There is no mechanism in our textbook, no mechanism at all proposed. And the second step is water. I'm going to put here not hydronium. Why couldn't it be hydronium in this case? Because if it was, you would end up with this. You wouldn't end up with an amine. You would end up with an ammonium salt. So not hydronium, because you would end up with this. And the carbonyl is basically just excised from the molecule. So you're kind of just taking a pencil and just erasing that off of there. So very interesting mechanism, but not covered in our textbook, therefore not required for this class. Let's try a couple of practice problems, and we'll take another break. Predict the major product for each of these reactions. The first one, this is something we saw at the beginning of the class today, acid chloride with excess ammonia. What are we going to produce? We're going to produce a primary amide. So we're going to end up forming the primary amide, which looks like this, NH2. And in this case, since you have excess, remember, the reason you have excess is because if you have HCl, the HCl reacts with the excess ammonia to give you ammonium chloride, right? The ammonium ion has a pK of around 9, whereas HCl has, son of a gun, HCl has a pK of around -7. So we end up with the primary amide and ammonium chloride from that reaction. And the next one is the hydrolysis of an amide with aqueous acid. We said it's a sluggish reaction, but it does work. And we end up hydrolyzing the amide to a carboxylic acid. And there's no way you could end up with this. You could not end up with that. Impossible, because you're in a strong acid. You end up with the ammonium ion, and that is one of the driving forces. I didn't go into the details last time, but again, the pKa of hydronium, gun. So as I was saying, is you end up hydrolyzing this to a carboxylic acid, plus you get the ammonium ion. If we look at the pKa's, the pKa of the ammonium ion is around 9, and the pKa of hydronium is around -1.7. So the equilibrium is going to lie to the side of the weaker acid. So it's going to lie to the side of the ammonium ion. Also, the carboxyl group is a weaker acid too. It's got a pK of around 5. All right, so that brings us to the last functional group section before we get into just hardcore synthesis, and that is nitriles. I think we deserve a little break, so why don't we take one?